Good morning. So today we are going to talk about mutarotation in the part of carbohydrate chemistry. So these things we have already learned in our previous classes, that where carbohydrate is present in our food, in our body, inside our body, what is the cell surface carbohydrates are there, and not even in our body, even some pathogens and microorganisms are also having carbohydrate in their cell. And how carbohydrate is to synthesize by the plant from the source of sunlight and carbon dioxide. These classifications also we have learned in our previous classes, that monosaccharide, oligosaccharide, polysaccharide. In polysaccharide there are homo and heterosaccharides. So today we will be talking about mutarotation. Before going into the structure, as per our previous class, can you guess what is the structure of glucose? Now, if I ask you this question, then the answer could be any one of these structure. Either it could be pyranose forms or furanose forms or in open chain form. But what is the actual structure of glucose then? That in a mixture, always there these structures will be in equilibrium. And how it is possible? Because glucose is having aldehyde moiety and several hydroxy moiety. Then in this structure, if you can remember what type of reaction, you know that in organic chemistry, when there is a aldehyde functionality and a alcohol functionality, there is a possibility of hemiacetal formation. And here, when glucose, in case of glucose, when that fifth position OH is participating in formation of glycoside, in formation of acetal, that case we can get a pyranose form. And if the position is getting involved, we will be getting a furanose form. And you know that when in organic chemistry, we have learned already that 6-member and 5-member rings are highly stable. So their possibility of formation of that bond is also more, or that possibility is better than other cases, as particularly for hexosugar. Okay, so how it happens actually? What is the mechanism? It is nothing but similar to that of the hemiacetal formation reactions. We have learned OH is going to attack to that particular aldehyde, and you will be getting different conformation. Now, if it is a 6-member hemiacetal, then that case there is a possibility that your OH may come above the plane or in the same direction with the 6th position OH group, or in the opposite direction. So we will be having alpha and beta, two different type of pyranoside in case of hemiacetal. And then what is the structure of that pyranoside? It is again, there is a possibility of mixture of alpha and beta hemiacetal will be forming if we have a 6 pyranose system in the glucose. And what is the alpha glucose and beta glucose? We call it when alpha means that OH is opposite direction of the 6 OH group, 6 position CH2 OH group, or in the same direction. If it is in the same direction, we'll be calling beta. Now, these two compounds are not same compound. Their physical properties are different. Their optical rotation is different. Their melting point is different. So these are the compound. This though they are forming in a same reactions, but they are called anomer. They are diastereomeric compound. They are one center. This is generating anomeric position. It is generating a center. If you closely look, that carbon is chiral now. So these cases we can expect that one chiral center is generating, means if we are not giving any influencing by any other parameters, then we will get alpha and beta both the components. However, as there are some other effects are present here, we will not be getting that 50-50 mixture, but some mixtures will be there. Now this is up to this, we can have a picture that when glucose is forming from open chain to 6-member hemiacetal forms, there is a possibility that it may have either alpha or beta glucopyranosides form. Now, these two compounds are different. They are diastereomeric. As the anomeric position is different, we call it anomer. Now, do you know that if we take pure alpha glucose, it has a specific rotation of 112 degree, and if you take beta glucose, which is having a specific rotation of plus 90 degree, if we either of the compound, if we mix in dissolve in water and take the optical rotation, it will change its value and we will have 52.5 degree. So if the compound we are dissolving in water, when we are dissolving a compound in water, ideally its conformations or its geometry doesn't change. So you may argue that when we are dissolving a compound into a solvent, there when we are not going for any chemical transformations, the optical rotation should be same. Yes, indeed, it should be same if it is the same compound. However, when we are changing, when we are dissolving one alpha or beta isomer into water, it is no longer the same compound. However, it is going to be a mixture of alpha and beta. How it happens? If we want to know, then we should go to the mechanism of formation of hemiacetal or middle. So usually how it happens? You have a OH group here, which is going to attack the aldehyde, and you are going to get this hemiacetal like this cyclic form, 6-member form. When in presence of water, we are going to in presence of water, what type of transformation, what type of changes are happening? It is acting, it is going through following mechanism, and then where there is a possibility that we are going to get proton from the sources alcohol, and our alpha and beta anomers are going to interchange between each other via a open chain structure. So what is mutarotation actually? The phenomena of the change of optical rotation observed when pure alpha or beta anomer are dissolved in water. That is how we can explain that. This because when it is D-glucose in alpha form, we are going to get the open chain form in presence of water, and that open chain form again going to distribute itself into alpha and beta anomeric form. That means this in water, this all will be under equilibrium, and that is the reason why we are getting when we are dissolving alpha form, alpha glucopyranoside in presence of water, it is forming the D-glucopyranoside from open chain form. Now, this open chain form is having two possibility. Either it can go back to that alpha form, or it can form the another isomer beta form. Now, in water, which form will be more stable? It depends that which direction the equilibrium will be shifting more. It is if it is we closely look that percentage of alpha will be 36% and beta will be 64%. This is due to this compound is more polar because of the oxygen dipole moment and this hydroxy dipole moment are unidirectional, making this more polar. And in water solvent, this will be more stable. So we can consider that 64% will be beta glucopyronoside. If we are taking only beta glucopyronoside, again in presence of water, it is forming the open chain form, and the same ratio it is going to form. So either we take alpha or beta in presence of water, both of the compounds are going to convert into the open chain form, and then ultimately we will have that 36% of alpha glucose and 64% of beta glucose in a mixture. Now we can explain that phenomena, that why when we dissolve alpha glucose, alpha D glucose or beta D glucose in water, then it will show the mutarotation. Now a big question, that whether methyl glycoside or any other glycoside, will it show mutarotation? Obviously not, because when it is acetal form, then that time if you want to go for open chain form, that is not possible without breaking that acetal form. Similarly, we can say no reducing non-reducing sugar will show mutarotation, as the interchange from the cyclic form to the open chain form is difficult for a non-reducing sugar. Only the reducing sugar whose anomeric position is free, that is, it is in the form of hemiacetal, will show the mutarotation. Now, I have a question for you, that can you draw the mechanism for the interconversion of alpha glucose to beta glucose? Not exactly the same way, whatever we have mentioned here. Okay, I hope I was able to give you some idea about mutarotation. Thank you.